Today's session, it's a generator and electrical machines special. We will have Emre first, talking about load cycling of generators. Then we have Kjetil, which will be talking about stability issues with higher share of inverter-based generation. And then last but not least, we have Eljesan, who is quite recently started PhD here, talking about investigation of losses in converter-fed synchronous machines for pumped storage hydropower. So 3 very good presentations. By that, I say, Emre, the floor is yours.
Thank you very much. Hello, everyone. Welcome to the first presentation of today. I will briefly talk about the results from our load cycling experiments that are exposed on generator coils taken after 43 years in service. Okay, let me just, yes. Okay, so before going into the details, I would like to refer to the people who were involved in this work. Of course, Espen has been the leader, and of course, Arne has been a very good discussion partner throughout the entire phase of this work. And several other colleagues from SINTEF have been laying the groundwork for this. And also Lars-Erik from MBE, which was involved in the, I think, removal of the coils. And some further assistance in the beginning of the work. So the content will start with background, and I will briefly talk about partial discharges, and I will introduce you the rig, some results, and summary and further work. So as an introduction, as we know, hydropower contributes to a stable grid, and expected lifetime of electrical machines or plants is around 50 years. But due to the continuous of most of the hydropower plants were the old ones were designed for continuous operation, but due to the recent intermittent way of running the energy network due to the penetration of renewables, we experience or expect more starts and stops. And what happens during a start and stop is that if the stop period is long enough, then the machine and the windings and core temperature can drop quite a bit until it started again. It just starts again, and we have some gradients and some time constants associated with all of these, and they're affecting the lifetime of a generator. And according to some old statistics from Sigre, 57% of the recorded failures are due to the insulation damage. Insulation damage is the insulation that is used in the stator bars that are applying the currents on the machines to generate force, the magnetic forces. And so the background is that what's the condition of the old generators given this intermittent operation, and can they withstand these more demanding operation strategy nowadays? So the work has started with the KSP project, Hydrostator, back in 2016. So there, I wasn't involved then, but I was involved in the last 2 years. I started at 2018 at SINTEF. And then Espen was coordinating with Arne, and in there were some removed coils or stator bars from decommissioned machines, and also new bars from other producers to test the condition of these installations and test them in laboratory conditions and expose them to accelerated aging to see if we find out some degradation mechanisms. And then activity continued on FME Hydrosen, also almost simultaneously, and there different coils were involved in the samples, and also some rigs were built from scratch to enable this accelerated aging. And by the way, you can stop me anytime if you have any questions, or you can wait until the end of the presentation, of course. And then this rig has been used in the KSP hydrostator, and then used in Hydrosan, and also its place has been changed here and there. It was first in the Sintef Energy Lab and then moved to Glashaugen later for NTNU students, like PhD and postdoc can also use them. And later, as the latest, of course, since we have the RenewHydro, it just took over this setup and then continue the research activities. And I will give more details about it in the upcoming slides. Like, what is a load cycling? Probably some of you don't know what the term really means, but it means it's the mimicking of starts and stops of the machines, exposing the stator insulation to this temperature gradients so that we can see if we detect some aging or some failure mechanisms. So like, I'm not sure about this statistic, but as a rule of thumb, we expect that 10 to 12 start stops per day are envisaged based on some statistics or some prior knowledge. And so as I shown you in the beginning of the presentation, there are some temperature changes in the windings and in the core in the machine. So since the windings consist of different materials, which are copper and the insulation, they have different thermal gradients. So when the temperature changes due to the different thermal coefficients, insulation material and copper just like shrink or expand at different rates, which will result in cavities and delaminations as shown to the right. So the more number of start and stops, the more number of temperature gradients, meaning there will be we are expecting more delaminations and cavities being formed in the insulation. And to mimic this, what we are doing in this setup is that we are increasing the temperature, and when it hits to a maximum temperature that the insulation class can withstand, we immediately start cooling it down and then repeat it. And by one cycle, as you see here, which takes about almost 2 hours, then we achieve one start-stop like in laboratory conditions. And then we just continue like that. And there are some standards that are, let's say, proposing some guidelines on this thermal load cycling, which is the current one is this IEC standard that is mentioned here. In there, it's only a thermal load cycling. There is no high voltage applied, and also it advises up to 500 load cycles. If there is no change happening, then of course it advises more load cycles, mean more starts and stops. But to make it more realistic, because in real life machines, while the machines are being exposed to these thermal gradients, high voltage is also present, right? So we thought these thermal cycling should be done under the presence of high voltage, and then when there is high voltage present while these cavities are being formed, there are some localized electrical discharges called partial discharges happening in those small, let's say, cavities or delaminations. The bigger the cavity, the lower the voltage or service voltage that you can get these discharges. And if these discharges persist for a long time, and then it will degrade the insulation. And there are different types of degradation mechanisms, but for us, the most relevant one is the cavity or delamination discharge. I'm just speeding up a bit. So yeah, so these cavities are forming between the insulation material and the copper, as I also shown in the previous slide. So a partial discharge is seen in a phase-old plot like this. So every single dot in this image refers to a single discharge event. So as you see, there are like millions of these dots, meaning millions of partial discharges happening simultaneously, all on these voids and delaminations. And over time, if they are exposed for a long time, it can grow or can just like lead to complete failure. And this is the green one, shows the voltage applied, and based on the patterns that we see, we can locate the let's say tell what's the source of the discharge. And this is a fingerprint of a delamination or void discharge. Okay, so like the results that I will show today is from a coils that are taken from Ovre Fiskenfoss plant, which was refurbished back in 2018, and we got some coils from them, and then yeah, just like adapted them in our test rig and exposed them to accelerated aging. So the first generation of the setup looked something like this, where we mimicked the stator core by using steel plates and confined the bars between those that also mimics the mechanical aspect. But this is only a single phase setup as a good start, let's say. I'm not gonna go into the details a lot, but like what we did here is that we used 2 bars and circulated a heating current in these bars, and we used a third dummy bar in which we installed some thermocouples inside the copper and outside of the installation to record the temperature. And whenever it hit the maximum set point, it stopped the heating current, and then it started blowing the fans, and it just like continued like that for the entire start and stop or like load cycling period. And then to adapt the Ovre Fiskenfoss coils, we had to cut these steel plates into 2, and then we have to attach them in a way that looks as realistic as possible. And in this also case, we tested 1 service aged, 1 backup wire, which was not used but stored in the same conditions in the plant, and we have 1 control or dummy coil in which we have installed some thermocouples inside. So then the test continued like that, and the experimental setup looks similar to the previous one. So the temperature control unit controlled the heating current and the fans based on the set maximum and minimum temperatures. So the early results show that over the cycles, we have seen some changes in the partial discharge characteristics. So the red ones show the applied temperature profile as shown previously, and the blue and green waveforms show the PD magnitude over the cycles. So like as you see, I'm not gonna go into too much details. As you see, some like these are also in logarithmic scale to the left. As you see, some higher partial discharge magnitudes are like starting to happen over the number of cycles increased, and also the higher magnitudes, let's say, start to happen at different stages. In the beginning, it was happening at the peak temperature. When we hit the peak temperature, we had the highest PD, but over the aging, after 2000 cycles, or maybe after 1000 cycles, we see that higher PD was happening during the cooling. So it tells us some, let's say, mechanisms changing over time. So to show the entire picture of the, let's say, degradation based on PD magnitude versus temperature, what we see is some unique hysteresis effects. And like how can it be summarized is that at the same temperature, we see different PD magnitudes depending on the heat, like temperature trajectory, if it's heating or cooling. So it means that the thermal coefficients of the insulation and copper are behaving differently from heating to cooling. So then what we are seeing is that although the same exact temperature was achieved, PD characteristics was following different trajectories. I'm not going to go into the details now, but we have a paper that is explaining all the mechanisms possible here, so I'm not gonna bore you with the details here. Also, like I want to show the entire, let's say, PD trends over the 2000 cycles here that were marked here. So the PD, average PD and maximum PD also changed over time, and towards the end we see some like quite abrupt increases that are signifying degradation. As I just mentioned, I think we think the change in the permittivity, also like the air conditions inside the cavities, thermal expansion, and everything makes structural changes and creating new voids and delaminations, and defects develop. And that's why we are seeing different characteristics in the partial discharge results. So, yeah.
Please, Emre, you have 2 minutes overdue now. So
no, we started the 2 past, so I'm now like 30. I have 30 seconds.
Good.
But yeah, I'll have two slides left. Like as also like while we were running the cycles, we also ran, let's say we stopped the cycles at given intervals and ran some offline measurements, which means we let the bars cool down to room temperature and then run some tests, and also saw some differences after some cycles. So then the question is, can offline methods capture the degradation or not? And the short answer is that they can show the degradation, but not at the same amplitudes. So our conclusion is that they should online or we call it on-cycle and off-cycle diagnosis should be combined, because they can't capture the unique hysteresis loops or effects that we find out throughout this work. But this work is also limited, like because this is a single phase. That means only one phase of current and voltage is applied. So it is falling short of replicating face-to-face electric field stresses in the end windings and interface electromagnetic forces that cause normally vibrations in the real machines. So to address these, we are now constructing a 3-phase rig based on the same logic, and it will bring in these effects as well to make it even more realistic. And the paper has gotten a minor revision, so I'm gonna submit it in a couple of days, so it will be available soon that you can read the details. Yes, that's the end of my presentation. I used 1 extra minute. Sorry. Yeah.
Well, thank you very much, Emre.
My pleasure.
Kjetil, he is ready.
Okay,
so take it away.
You. Yeah, do you hear? You can hear me well?
Yeah.
Good. Just have the pointer here. So this, I'm going to talk about stability issues with higher share of inverter-based generation, and this is a subject that pops up in different discussions. So I thought it was could be relevant here as well when you discuss. So this is sort of my view on the topic then. So first, what are inverter-based resources? Well, I'm thinking that it's all the components that are connected to the AC grid via power electronic converters, and this, as you know, can be on wind turbines, wind farms, photovoltaic system necessarily, battery energy storage, but also on the load side, variable speed motor drives, aluminium smelters that they are connected. There are converters there, and all kinds of loads, really, including electrical vehicle chargers. But a focus here is on voltage source converters, I would say. So, what are the issues? Well, synchronous machines are connected to the grid and synchronized. And the control of the power plants that are synchronously connected, we control the power frequency with the turbine typically, and the voltage reactive power via the magnetization system of the generators. But for converters, the synchronization and the control is all by through the control, you could say. So, and to quote one of my colleagues, these control systems can be anything you like. Said not everything, but still there are very many ways of controlling converters. So as a motivation, the power system is changing, and because the power electronics is changing the dynamics and the inherent characteristic of the power system. You see, we always had we always in the society have leaders and followers, and that's also the case in the power system. But all these followers that we have today must become more kind of leaders if you think about wind and solar and those things. But the power electronics here is also an important part of the solution. That's what we're going to discuss. So the issues that I'm focusing on here is inertia, together with the active power balancing, voltage control, which is the reactive power balancing, you could say, and issues related to short circuit capacity, such as impacting fault ride-through capabilities and protection. Starting with the inertia and power balancing, you could say you can learn a lot by looking at measurements when there are larger disturbances. In this case, there was an outage. I think it was the nuclear power plant in Finland, Olkiluoto. And you see the response in frequency, the drop, and how it stabilizes. And out of this, we can read something about the primary reserves, what we call in the Nordics regulærstyrke, to contain the frequency, the frequency containment reserves that is activated. But we can also see something about the inertia or the kinetic energy in the system. And of course, the importance of the kinetic energy is to maintain the balance in the very short term. And if we look at the rate of change of frequency, as we say, the rock-off, we can estimate how much kinetic energy we have. And in this case, it was fairly good, about 250 gigawatts seconds. But then what happens if we disconnect a large amount of the synchronous resources? The inertia will, of course, be lowered. And this is just some simulations I did to sort of verify where we are today based on events and what could happen if we drastically reduce the inertia. We see that if we can accept the voltage, the frequency drops, I mean, we can still maintain the balance. But there are some issues. How do we, what kind of frequency deviations can we accept, and what are the measures regarding control? There's another one that shows maybe the same. What are the mitigations here? We need, my sort of conclusion is that we need faster control. And faster control is possible with inverter-based resources when we have sufficient reserves, of course. And if we don't, in combination, for example, with battery energy storage. Of course, since we are in RenewHydro here now, the better utilization of hydropower plants is also something to look into. Can we utilize, for example, the run-of-river power plants more to provide primary reserves and fast control? And again, the demand-side flexibility is, of course, important. One questions that you can think about is today there's sort of one tries had the requirements to maintain the frequency within plus minus 0.1 hertz. Is that necessary? Would it help if we relax that sort of frequency band? I'm not so sure, but it would, of course, involve some changing of relays and so. But maybe there's something to gain. I'm not going into this, but just to show various controls that are proposed for grid forming control of converters. So you see this is in a way to mimic the response of a synchronous machine with its inertia. So it would be virtual inertia, but you sort of control the power balance by that, and you have a voltage regulator loop on that. It's something to look into. Stepping to voltage control, the reactive power balance. This is, of course, a topic that has gained a lot of interest after the blackout in Spain and Portugal, where you see that the voltages came out of control in a way, and a lot of generation was stripped due to that, and it ended up with in a collapse. And you could see sort of, this is from the final report from that event, how when voltage, the relationship between voltage rise and loss of generation, which is a little bit uncommon way, but it signifies the need to control voltages. And then again, the solution, I think, is very much also on the inverter-based resources themselves. If we look at PV plants, was that consisted, it was a major part of the generation in Spain that day. I mean, if we look at the controls here, it's nothing. It's quite easy to also add the voltage control loop that can provide reactive reserves in both ways, in addition to, of course, the maximum power tracking of the PV plant itself. So lastly, a little bit, some comments on short circuit capacity. In my view, this is about voltage and current sensitivities, and also the selectivity. I mean, if you have a strong grid with low impedances, you need a lot of current to control the voltage, and you can easily control the voltage. So you don't. On the other hand, if you have short circuit, you would need some currents to detect and isolate that fault. So that impacts what we call the fault ride-through capability of the machine, that their ability to maintain synchronism when there is a fault. And consequently, it also affects the protection and design of settings of the protection. So just some examples I used to show in my lectures, or in part of the lectures. I mean, here you have, this is one generator connected to a grid, 40 megawatt generator. You have a three-phase short circuit lasting cleared after 150 milliseconds. And you see you got the power swings, but it remains stable. If I sort of delay the clearing to 170 milliseconds, you lose synchronism. So that is sort of also one of the motivations for having requirements on fault ride-through, this is from the Norwegian requirements by Statnett. And you see here that it's we require that you can sort of ride through faults that on the high voltage side go through zero and maintain for 150 milliseconds. So in this case, my generator would fulfill the requirements, but this is quite tough. And the reason why it goes to zero is, of course, that with less short circuit current contributions, you will also see more a risk of voltages going down to zero during a short circuit. So I can just sum up, and we have time for some questions maybe. In my view, this is all about control and the available reserves, of course. When you don't have any reserves, there is no no way. I mean, that was clearly shown in the Spanish blackout, where there was no reserves to maintain the balance. So we need faster control to take that, and we need reactive reserves and reliable voltage control on the IBRs to maintain security in operation. So maybe we need to look more into the aspects of short circuit capacity. What are the impacts? How can we ensure fault right-through capability? And maybe to some extent we need to rethink the way we do protection and selectivity, and also maybe also the requirements on frequency. So that was very quickly what I wanted to bring in here. Thank you.
Thank you, Kjetil. So, Eljesan, are you ready?
Yes. Okay, so hi everyone. I am Eljesan Ibrahimi, first year PhD student in electrical machines. And my research topic is the investigation of losses in converter-fed synchronous machines for pump storage hydropower. So we're going to go through variable speed operation of pump storage plants, converter impact on synchronous machine losses, research planning, and ongoing experimental work. So what are the reasons for choosing variable speed operation instead of fixed speed operation? We have three main reasons. The first and most important one being the regulation of power in the pumping mode. Then we have the faster turnaround and the grid support. So we're going to see how these three reasons connect to each other. Here we have a representation of a pump storage plant, and we know that it works in two directions. One is when water is flowing from the upper reservoir to the lower reservoir. This is the turbine mode. Here water is spinning the turbine, and we are generating electricity. And the reverse operation is when we're absorbing electric energy from the grid. The turbine is circulating, or let's say pumping the water from the lower reservoir to the upper reservoir. And if we take a closer look at the powerhouse, we can see individual components. We have the electric generator, or the electric machine, let's say. We have power electronics and transformer. And we know that in fixed speed systems, we regulate the power that we are generating by using a system, a governor systems, which consists of some gates, which allow water to flow inside the turbine. And by opening and closing these gates, we actually control the power that is being generated. Okay, so what about pumping mode? Well, this is simply not possible in the pumping mode because the turbine is driving the water, and if we try to restrict the flow of the water, then we move the turbine in an unstable mode, and we can damage the turbine. So this is the biggest issue, and how do converters come into play here is by allowing the turbine and the generator to spin in a different speed by decoupling the generator from the grid. And in this way, we can also have a fast transition time from generating to pumping mode, because now we don't have to disconnect the machine from the grid, but we can stay connected with the converter, and we can supply the grid with reactive power, maintaining a stable voltage while doing the transition from generating to pumping, or vice versa. Why is this problem actually emphasized? It is because of the higher share of intermittent sources like solar and wind, whose generation can be unpredictable. And in this way, if we end up with more generation than consumption, then some of the plants must be shut down. So it is not a feasible way to either shut down a plant or just shut down another plant. So it is not feasible in both sides, in the view of the plant itself and in the view of the grid operator. So this is how converters come into play and actually solve this kind of problems. Now coming back to the generator itself, what is the impact of the converter operation on the synchronous machine? Well, it increases losses, and as a result, the machine heats up, and this means we have a decreased efficiency and lifespan of the machine. So this is a problem. And how does this happen? Is by the converter operation. Here we see an ideal sinusoidal current waveform, which we can produce with the generator without the converter. It is not, of course, ideal, but it is very close to this waveform. So how the converter operates is it switches the current on and off many times per second, and this creates a small deformity in the current waveform. And what does this mean? It means that now we don't have just the 50 Hertz component of the current. Now we have some currents with higher frequencies. We call higher order harmonics. And the problem is that the machine is actually designed for 50 Hertz. It is not designed to handle this kind of frequencies. And we all know that most of the hydropower in Norway is actually old. So it is not maybe so preferable to design a new machine. So the idea is to actually upgrade or retrofit the existing plants. And how do these higher frequency currents correlate to the machine? We have two main ways. One is by hysteresis losses, which are proportional to the frequency, and we have eddy current losses, which are proportional to the square of the frequency. Of course, we can see that the majority of the losses fall on the eddy current losses. Okay. So what is the general plan of my research? Of course, always the first step is by measuring these extra losses in a converter-fed synchronous machine. Then we'll try to develop and validate loss calculation models, and then we'll test these models for large-scale machines from real power plants, compare different types of converter technologies regarding these losses, and then in the end develop mitigation methods. Okay, so what is the ongoing experimental work? This is a bit of an older picture of the setup that we have. I'm sorry I couldn't secure a recent one, but it's the same. It hasn't changed much. So here we see the gray machine, which is our synchronous machine, which is the subject of our research. This is a scaled down version, a 100 kVA machine. It is a scaled down version of a real case machine of 300 megawatt of power. And this synchronous machine is connected to this induction machine via this shaft and gearbox, which actually makes the speed, matches the speed of the induction machine and the synchronous machine. Why do we use this induction machine? Is to actually simulate the reversible pump turbine. So the control system of this machine is connected to the water laboratory via high-speed fiber optic cables, and we can get real-time simulations from the turbine side. And of course, we have the converters on both sides of the machines, and we can connect the machines either directly to the grid or by using power frequency converters. Okay. So right now we are on the step one of our experimental stage, where we're trying to accurately measure no load losses, and we are setting up the experiment and verifying, and we are calibrating instruments like a high precision torque meter, and then from the measurements we're trying to make a separation of different type of losses. So for the moment we are at this stage, and we are going to do maybe a few more experiments just to make sure that we are measuring correctly everything. Then from that we'll move to measure the extra losses from the converter, then do a computer simulation with a finite element method, and in the end we'll try to interpret the results. So right now there is not much going on in my work as I've recently started. So this is all that I have for the moment. Thank you for your attention.
Thank you very much, Eljesan.